Hey, hello everyone. Good morning. I'm sure you all are able to hear me and see the screen as well. So, Enoch, would you want to give away the prize?
Yes, Barney. I'll do it.
And also, I request you to do two things every day. And also, please share the YouTube video link. Have the people also subscribe. Yeah, over to you, Enoch.
Thank you, Barney. So what I'm going to do is first I'm going to share the YouTube playlist link where you can subscribe and watch the replay. Now, yesterday we posted a few quiz questions on a couple of our platforms, and we've collected the names of all the people who have participated in it. And we have about 176 people who participated in it, and we are going to use Google's random number generator to pick a random person and then give a surprise gift. So we have the total of 176 people, so I'm going to put minimum of 1 and the maximum of 176, and just double checking it. And the moment I click on generate, a number would be generated here, and the person corresponding to this number is a winner. So without any further delay, let's do this. 3, 2, and 1, go. So it is number 60. So let's see who the lucky person is. It is Dilip Kumar Koda. So Mr. Dilip Kumar Koda, congratulations. You are our winner for today. And we will get in touch with you, and we have your details. So we will take your details and we'll get in touch with you, and we will give you the surprise gift. And for those of you who are wondering where can we find the replay, yesterday's video and all, so on your chat, on top of your chat box, there is a sticky note which should be in this yellow shade. We pasted the details here, so you can just click on this link and that will take you to the YouTube playlist. So I'm going to show you the playlist. And this is our YouTube playlist. You can see that all the days are updated. Today is day 15, which would be added to this list shortly. And if you're not subscribed to the list, I would recommend you subscribing to it. There will be a button here as somewhere around this area which says subscribe. So please go ahead and subscribe. And over to you, Bernie. Okay, let me check. So now can you see my screen, everyone? Please confirm. Okay. So when you click on this link, it will take you to a playlist like this. And within the playlist, here you will have a button to subscribe. So when you click the subscribe button, you will be notified of all our videos that we are going to upload. And this is the playlist that we have, and you can see that we'll be adding the day 15 here, which will be today's video, will be added here in the next maybe 15-20 minutes. And yeah, over to you, Bernie.
Yep, thank you so much, Enoch, for this. Let me now ask a poll question on: are you all able to see the screen? Yes or a no? Please, can you reply on whether you are able to see the screen or not? Wonderful. And I should also tell you that I keep doing the speed test just to show you all that this has some problem. I think now speed test. It's directly there here. So I click on run. Look at that. My internet speed is of approximately 100 Mbps. download speed and again, if you have any issues, you might be aware that issues are from your side. Okay, so please fix your internet issues and audio issues. And here is a YouTube playlist. T. Chandrasekharan has actually given that. This is day 14. Okay, and we will have another. What today is Tuesday, so we are going to have the session until 28th. Right. After today, there'll be 5 more days. So in total, it'll be 30 days basically. Yeah. So sorry, today is I think day 15, right? And yep, this is how it is. Day 15 session, and we are discussing about recurrent neural network. So let me proceed here to the mind map. This mind map today will once again upload on our system, on our website. So you will reap the benefits. So here we have neural network. And today we are going to switch to recurrent neural network. But even before we proceed further, we had a brief overview about text mining and natural language processing. Yeah. We tried to understand the difference between these two. And we discussed that text mining is all about dealing with text, unstructured textual data. If you analyze it, then that's called as text mining. And then we also have speech processing, which is NLP. NLP is all about dealing with unstructured data, both which is in textual format as well as audio or speech. Okay. And then we have also discussed yesterday that NLP has two categories. And those two categories are NLU, which stands for natural language understanding, and NLP, which stands for natural language generation. Oops, sorry, NLG, natural language generation. Na- Natural language understanding means you give an instruction or you talk to the robot or inanimate object like your computer system, etc., and the system or your computer would act accordingly. NLG is your robot or machine or system would hear you, and it will also respond back to you the way human beings do, right? And I've yesterday shown you the video pertaining to robot. Then we discussed about data preprocessing. And then after this, you will say, wow, deep learning is like awesome, right? Because all these things would be automatically performed using your neural network. But then why don't we use that? It's going to be very, very time consuming, and tons of data, right? So in certain cases, you use deep learning. In certain other cases, you machine learning algorithms. Okay. In data pre-processing, we discussed about tokenization, and we discussed that tokenization is all about splitting the sentence into constituent words. Then we have also discussed about the three types, right? You have basically the three types: unigram, bigram, trigram. If in n grams, n is greater than 3, then we do not have so much of compute. It is time consuming and costly affair. Okay. And then we have parts of speech tagging. This is also called as post, or it is also called as grammatical tagging. These are the different names of your post tagging. Then we stop word removal. Then we discussed about text normalization. And text normalization can be performed using spelling correction, stemming, lemmatization. Lemmatization does an additional check of what is in the first place stemming. Stemming is all about bringing the words to their base form. Like if you have playing, it makes it play. It says that it's play. Then we have lemmatization. Lemmatization is an additional check. This technique does an additional check by looking through the dictionary. So it will look through the dictionary to find the base form of the word. Then we have named entity recognition. Okay, which will extract what? Names of people, places, organization, quantities. Okay. Then we have something called as word sense disambiguation, wherein the words in different sentences will have different meanings. Okay, and then we also have sentence boundary detection. Okay, and when it comes to tokenization, you can make use of regular expressions. You can make use of text blob. You can make use of keras. Okay, and we will be making use of keras. And there are also various types of tokenizers, which we have discussed. One is tweet tokenizer. Another is MWE, which is called as multi-word expression tokenizer. Then we have also discussed about regular expression tokenizer. Then we have discussed about white space tokenizer. And we have also discussed about word tokenizer, punctuation basically. And then we have also discussed about stemming, which we haven't mentioned here, I think. Yeah. Oh no, in text normalization we have discussed. Yeah. Stemming. Broadly, there are two methods. Method one is called as regex, regular expression stemmer. And another thing is quota stemmer. Then we have discussed about lemmatization. We discussed about um, singularize or pluralize the words or pluralize. Then we have also discussed about language translation. Okay, and then of course we had stop word removal. And then we started discussing about feature extraction. So data pre-processing, then we discussed about feature extraction. How do you manually extract the features from your textual data? The most raw form is number of words. Then you have polarity score, subjectivity values or score. Then we have bag of words representation. Then we discussed about Zipf's law. What does Zipf's law say? Frequency of any word is inversely proportional to its rank in the frequency table. Then we have TF-IDF. Term frequency, inverse document frequency. You also have term frequency for that case. This is also another feature that one can extract, and this is term frequency inverse document frequency. Right? And then we have also discussed about how to find out, this comes under feature engineering, how to find out similarity between text documents. There are two things that we discussed. One is cosine based similarity and another is Jacquard similarity. Okay. And then we have also discussed about data visualization. How do you visualize the data, right? In this, you can represent the data as word clouds, or you can have other visualizations such as dependency parse tree, and then we have named entities. Of course, there are many other things that we can go on and discuss, but then we have to draw a line and do justice to the amount of time that we have. So we will now get into recurrent neural network. Watch the recorded videos at least 2 times and run the code by typing it. Do not use a, we will very soon upload the files, datasets, and we will also upload the code on the learning management system also. But then a word of caution: if you directly use it, you may or may not able to um, you know learn programming language. Okay. One more thing is, we have done this analysis for a company called as Cat Center. We have taken the data from their quality assurance and customer satisfaction. There were 11,783 students feedback. Okay, that was done in 2017, and one of our chief data scientists was involved on this project. Okay, and when we analyzed 5,848 lines of feedback was there, we have done a positive versus negative word cloud. All these are the things which are possible. I'm just explaining you about practical application because a few of you all were asking for this. And if you look at 2015 until 2017, green and red color were very similar. I mean, almost the green color and red color is the same. Ideally, for any organization, over a period of years, you expect the positivity to increase and negativity to come down. But it was almost the same, so that was a bit alarming. And then we have done polarity plot, sentiment polarity plot, wherein this is 0. Any number which is above 0 is a positive number, a positive word. Any uh, word which is below this is a negative word. You see a spike over here. If someone says, hey, your training is good, say you give the feedback on the last day of the training, right? We'll share the links where you can give the feedback. And if you say training is good, okay, but if you say training is awesome, right? If you say training is awesome, then this awesome will have a spike like that. If someone says, you know what, your training is bad, it will have a negative word. If you say your training is pathetic, then it will have a peak like that on the negative side. We can also do semantic network. I mean, you cannot possibly read 11,783 reviews. It's a waste of time. Not that you cannot read. It would take a lot of time. That is called as brain drain, underutilization of human capital, intellectual, your brain. Okay. Hence, we have done this. Very quickly, it gave away the entire story. For example, a lot of people were raising complaints such as they had issue and they were saying, kindly provide the certificate. And that's the issue that they were facing. Another problem is instructor or faculty were clarifying the doubts. They were good and experienced faculty, right? Wonderful. So you have to spend some time. It's not easy just looking at this and drawing some insights, but then it quickly um, gives away a lot of interesting insights. Yeah, very, very important. Semantic network. We have that included as part of our training curriculum in data science. And then positive word cloud. What are the things which are positive? What things are people speaking about? Right? What things are people speaking about in a positive manner? We have done cluster dendrogram. Staff is good. Staff is excellent. And then we have done a bigram. And then when we have done this, a lot of people were saying problem, doubt, worst, bad. But but then when we have read this in context, we found that a lot of people are asking for more practical problems and solutions to the problems. Majority of them were giving such feedback. And when we have done this trigram, 3 words, haven't received certificate, staff is helpful, friendly, receives a majority of them was speaking on the lines of certificates. They were saying, hey, certificate, that's the challenging area. Then we have done a scree plot and we have done additional clustering. Okay, and then we have done emotion mining. How many people are negatively writing about you? How many people are positive? Majority of them are positive. That's a good thing. And what kind of emotion they had? Whether joyous, sad, angry, fear, surprise, disgust, we felt that majority of them were joyous. Then we have also done something called as emotion mining. In 2015 March, a lot of people were writing negatively about this company. And then they have taken some corrective actions in May 2015. They moved towards the positive zone. They enjoyed the positivity. And then again, they jumped into negativity. Again, they started experiencing the positivity. Again, it dipped. Okay. So all these are a few amazing things that we have done as part of our project. So I just wanted to show that because a few of you all were expecting, practical stuff to be shown. And did I also show you the cancer dataset? Did I speak briefly about that and then show you the dataset? Can you throw some light? Okay, just looking out on where that image is. I think sample images. Yeah, radiology and pathology images. Did I show that, friends? Can you please comment? No? Okay. So I was showing that, I worked on a project wherein we built cancer prediction model. Right? I've shown you all these images, if you remember, dense, benign. Okay, these radiology images. I've shown you this also, if I'm not mistaken, right? If I haven't shown, I'm showing you now. So these are the images, friends. So these white spots that you see are called as calcification, microcalcification images, right? And we have MLO images, left MLO, right MLO, and then contour masking, the computer vision and image processing aspects that we have looked at. We have these things. Okay, you can do a Gaussian blur, and then you see that spot there. There could be that could be cancerous tumor basically. Okay, we can do those things. And then these are the various classes. We didn't just classify on whether an image is cancerous or not. We actually looked at 10 different classes. Class 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. There are 10 classes overall. Okay, so it was classifying all of that. And all these are the various images of different types of cancers, tumors, right? CC, MLO, all that. And then, of course, I think there was also here. Let me go to that sample images. There is also this pathology image. As I've told you, if there is any suspicious cancer symptoms or tumor, and if radiologist is not able to identify that, then they send your tumor for biopsy, and pathologist is going to analyze that. This is that image. I can also show you one more thing. Okay, and that is this one. So please bear in mind that this particular image is called as whole slide image. The entire image will be of 1.5 GB, right? But then what we have done is we have taken only the regions of interest like this, and those regions of interest, we have again broken down those into tiles. We made it small, and then we try to analyze that. And these tiles is what these images are of. Okay. Benign means non-cancerous kind of. So this is how the tumor looks like. Okay, and then you analyze it to figure out what's happening in that tumor. And malignant means cancerous. If you put this cancerous part beside non-cancerous and then try to analyze, you will be able to make out to some extent. Of course, you're not pathologists or I mean proper MBBS doctors. They after MBBS they do a specialization on radiology or pathology, right? So we cannot match them, but then yep, some kind of knowledge transfer will happen. That is called as osmotic uh, communication. We have done that also, Aparna. We have done for lung cancer also. We worked along with Apollo hospitals. But then after Indian government directive that we should not be working on anything related to COVID-19, we dropped that idea. But it was also appreciated in South Korea. Okay, back to our discussion now. Recurrent neural network. So until now, we have discussed about CNN, convolution neural network, and now we are discussing about recurrent neural network. So we have traditional language models. First, we will talk about that, and we'll discuss on why we shouldn't use multi-layered perceptron. Then we'll discuss about RNN, what are the various types of RNNs, CNN RNN model, bidirectional RNN, deep bidirectional RNN, LSTMs, deep recurrent neural networks, deep LSTMs. You will learn about all of these. Okay. So sequences, whenever you have sequence of data, it could be sequence of characters, sequence of phonemes, sequence of words. Whenever you have a sequence and whenever you have some time series data, you can apply recurrent neural network and its variants. RNN and its variants can be used. For example, it can be a character. For example, after F, O, R, E, what comes next? What comes next? Which character comes next? You can predict that. You can also predict on which word comes after which. Next word prediction problem sequence. If you're speaking something and suddenly there was some noise and the other person wasn't able to hear that, then especially in armed forces, what happens is people, our army or the armed forces, Navy, Air Force, etc., they sometimes are at a specific location from where getting the signal would be very difficult. And constant communication is very much needed in those kind of scenarios. If certain words are not heard properly because of noise, then those things are auto corrected live during the transmission. When the voice is being transmitted to you, when the other person speaks, then you'll be able to hear that properly. The noise gets automatically rectified by using these kind of algorithms. It's very, very dangerous, because if someone is saying don't go on va, if don't was a word which wasn't heard properly, there'll be a var. People will go on va. So it's very, very important, and accuracy should be almost 100%. Okay, very important. That's the reason why, though they use such things, they also make use of human intelligence. Okay, it can also be used for language translation. When you have something written in German language, okay, and then if you want to convert that into some other language, English for example, you can do that. But the only thing is the sequence in which words are written in German language and the sequence in which it is written in English language, the sequences are not the same. Okay, this is also another thing. Now, whenever you have this kind of a data, wherein you have sequence of words, sequence of characters, right, sequence of sound, speech, sequence of language words, you can use traditional language models, or you can use your multi-layered perceptron. But then let us understand on what are the disadvantages with respect to these models. Let us first understand about language model. A language model is all about computing probability for a sequence of words. Okay, it is useful for many tasks, such as it is useful for next word prediction. If someone says stocks plunged this morning despite a cut in interest rates by the Federal Reserve, as wall. After this, what should come? Street. Wall, street. So you take all the articles from Wall Street Journal or Financial Times or the Hindu or the Times of India, etc. Usually the literature and the English grammar, etc., is very good. Okay, in these kind of prestigious media houses, and you take each and every word or each and every sentence that appears, and those sentences will be your training data, and you train on that. Okay, it can also be used for spell checking. They are leaving in about 15 minutes to go to their house, and this has to be automatically corrected, or at least below this there should be a red twiggly like that. Then you right click on this and then decide, and then you say it should be minutes. You also have mobile autocorrect, right? He's trying to find out. It's not find, right? These kind of things also are applications of language models. Speech recognition. If you're talking and if you say theater owners, I mean you're say a journalist who is passing on the information to the media house. If you say theater owners say popcorn, sales have doubled. Or if they use unicorn, you know that it is not unicorn, it should be popcorn. Automatically such things are corrected. Automatic essay grading. Professors lecturers, this is something that we have already done. Okay, for our own learning management system, we have done this. Wherein, when our students submit their assignments, we run it through our algorithm, which will automatically grade. Okay, it will ease out a lot of time, right? It will make your life extremely easy. And yeah, if you as a college wants to have this kind of application, do reach out to us. Reach out to me. We'll be more than interested in doing that project for you. Of course, it'll be a commercial project only, but then it includes a lot of AI aspects, right? It is used heavily in all the entrance exams such as GMAT, GRE, IELTS, TOEFL, so on and so forth, right? And that is how analytics is used. Then we have machine translation, word ordering. The cat is small versus small the is cat. Now we look at what is the probability that the cat is small appears in that sequence, and what is the probability that small the is cat appears in that sequence. Obviously, this sequence will have higher probability, and that's used for ordering the words as well. That's called as machine translation. You just set of words, and if you want your algorithm to construct the English sentence in a proper manner, that can be done. Walking home after school versus walking house after school, what words would appear? Choice of words: home versus house. Which of these has more probability? Obviously home will have more probability. That's how you consider. And then you have traditional language models. Traditional language models, as I've told you, depends heavily on probabilities. For example, if you have a bigram word and say you want to predict on what will come, or what is the probability that you'll have language given that you already have the word traditional. Okay, what is the probability that you'll have the word language given that you already have the word traditional? Here, how do you calculate it? You just say count how many times word 1 and word 2 appear together, divide by, this is like W2 and this is like W1. And you want the probability of this. Probability of word 2. What is the probability that it will be language given that it has the word traditional? If you want to solve it, you say count how many times these two words appear together, divided by count how many times traditional appeared. When you do this, you get probability. This is how the bigrams are formed: two word clouds, etc. Then you also have trigram models. If I take this sentence as an example, okay, then how do you calculate? Probability of word 3 given word 1 and word 2 already occurred. This is called as conditional probability. Okay, this is called as conditional probability. What is the probability that word 3, which is models, appear given that traditional and language appear. Okay, given that traditional and language appears together. This is what um, traditional language model is all about. But the disadvantage with this is the number of the amount of compute that you need will just get exploded. Why is that so? Yeah. Why is that so? Because in English language, in English vocabulary, we you'll have 172,000 words approximately. That's the size of vocabulary. If you want to form unigrams, single word words like traditional is one word, language is one word, models is one word. When you want to do this, you need to have 172,000 words to handle. If you move from unigram to bigram, then what will become to the size of this vocabulary? How many words will you have? This is a question that I want you all to answer. And here we go. Poll question coming your way. If we want to form a bigram, then what will be the size of vocabulary? Will it be V or will it be V square, V raised to the power 2? Okay. Or will it be V factorial? What do you think is the right answer? Yep. Please, can you all answer that? Wonderful. Almost 100% of people are responding in that way. Yep. And now it's reflecting the right picture. No, guys, it's V square. Take here only the example. If you want bigram, it's traditional language. This is one word. Traditional models is another word. Language models is a third word. Bigram will also have unigrams, right? So you'll have traditional language models, right? So you'll have V square. If I want to run an n-gram model, or let me take trigram before that. For trigram, it will be V raised to the power 3. 172,000 into 172,000 into 172,000. I mean, that would be like huge data. And if you proceed with n grams, it'll be V raised to the power n, which will just explode. And people, when they have done a research, one machine with 140 GB RAM for 2.8 days, then they were able to do tokenization alone. They could only form a tokenization. Tokens. Okay. Now, you consider a case where an article discusses the history of Spain and France somewhere in the first paragraph. Okay, somewhere in the first paragraph, history of Spain and France was discussed. Now, somewhere here it says the two countries went on a battle. Now, which are these two countries? Say in the 10th paragraph, you have a reference of the two countries. And in the first paragraph, it says history of Spain and France. How would your model understand that the two countries here means Spain and France? How do you know that? Right? There is no way that you can know about this when you perform the traditional language model technique. When you apply such a technique, there is no way you will be able to understand. Hence, we are going to proceed further with the next algorithm called as MLP, which we have already seen. So here, if you have n gram, then the size of your vocabulary would become v raised to the power n. Those many tokens will be there. So much amount of memory is required. Too much, right? Too much of memory is needed. Okay. Hence, we resort to MLP, which is multi-layered perceptron. When it comes to multi-layered perceptron, you have a neural network kind of architecture here. How does this neural network kind of architecture work? Let us understand. If you have three words such as original, neural, network, and say you want to build the fourth word, then you can apply MLP, multi-layered perceptron. And how does your underlying data look like? There is no dearth for data here, okay? So you go to any good English news channel, pick up the words, sentences from there, split them into four words. Okay, x1, x2, x3, and the last one will become your output variable. If you want to predict the fourth word based on three words, then this is how the data set would look like. So you say original, neural, language, model will be here. So you generate this kind of a data set, and getting this kind of a data set is extremely easy. It's very unlike your images. Okay. Then we'll discuss about the disadvantages later, but let us first understand on how this works. So you take the first word, okay, and you do a one hot encoding on that. What do you mean by one hot encoding? You take all the 172,000 words that English literature has, 172,000 words. Put it 1, 2, 3, 4, 5, 6, 7, 8. You have all those 172,000 words, and you keep putting 0, 0, 0, 0, 0, 0 throughout. And wherever you see this original, you put a 1. Rest will be all zeros. Okay, then take neural. Do the same thing. Take all the 172,000 words and take all those words. This one is not neural, not neural, not neural, not neural, not neural. I mean, like this. And wherever you find this term neural in the English dictionary, you put a 1. Rest all will be again zeros. Do the same thing with language also. So what happens is the size of this will be V vocabulary, number of words. So V. The size of the second also is a complete size of your vocabulary. You put all the words, and wherever you find neural, put a 1 against that. So this size also will be V. And for language also, take all the different words of English literature, put all zeros, and wherever you find language, put a 1. And if you have n such vocabularies, then it becomes NV. If you have n, okay, those many are there. And say you have 1,000 neurons in the hidden layer, and I'm giving H to this 1000. So how many weights will your model learn? Here, if you have V, that means 172,000 words here. It is, that's the English literature V into H. So this every neuron will be connected to every other neuron. Every neuron will be all these 172,000 neurons plus one bias would be connected to all the neurons in the hidden layer. So how many weights will your model learn? For one input, it will learn V into H. For this also there'll be V into H. For this also it'll be V into H weights. And if you have N words, then it'll be N into VH. Those are the number of weights your model is going to learn. Okay, so you have V, and H. Now the final output layer will also have size of V, because you want to predict the fourth word. So throughout, it will be giving certain probability values. Okay, and for this word called model, it will have the highest probability. So in that way, you predict on what is this fourth word. And this will be a size of, this will have a size of V. So plus number of weights that you're going to learn here will be V into H. Okay, number of weights that you learn here will be N into VH. And here it will be V into H. So if you were to write it, it'll be N plus 1 into VH. NVH plus VH. These are the number of weights. If you look at the previous scenario, V raised to the power N would have been super crazy. Here, at least the number of weights have come down significantly. That is the advantage of multi-layered perceptron over your traditional language model. But then there is also disadvantage here. The disadvantage is that if you're building a model in such a way that you have 3 words as inputs, and if you want to predict the fourth word, okay, if you have 3 words as inputs and if you want to predict the fourth word, then it will work only for this setting. If you have 2 words and if you want to predict the third word, then you need to build a different model altogether. You have to build a different multi-layered perceptron. If you have 4 words and if you want to predict the fifth word, okay, if you have 4 words and then if you want to predict the fifth word, then again you need to build another model. So in this way, how many will you build? Right, this is another challenge. So the problem is it has a fixed window of context. If you build using 3 words and want to predict fourth word, it will work only in this setting. 4 words and predict the fifth word, it will work only in this setting. Okay, so it cannot capture different window widths, different window contexts, different you know words, length of words and predicting the next word. It cannot work. It doesn't work. This is one challenge. Another challenge is it doesn't store the previous words in memory. For example, in the first paragraph, people discussed about history of Spain and France. Say in the 10th paragraph, it says the 2 countries. Now, if you don't store this information of first paragraph in memory, you would not be able to handle this scenario. And when your 10th paragraph says the two countries, you don't know what those two countries are. So two challenges. One is it works on the fixed window of context. That means it does not work on variable window width or word length. First disadvantage. Second thing is it does not store the history of what has been referred to in the past in memory. Two great challenges. There are two big challenges here. Okay. But then when it comes to number of weights, if you have V into H and if you have N V's, then it'll be NVH plus H into V. So this will be N plus 1 into VH. The number of weights are significantly less than your traditional model. But how do we overcome these two challenges? And can the number of weights be decreased even further? Is a question that data scientists embarked on. And then finally they came to a conclusion that recurrent neural network will be an amazing model which will solve all these kind of challenges. And we are going to discuss about all these kind of challenges and how do we overcome using recurrent neural network. One thing is in the recent times, what has happened is when you search in your libraries about RNN, your libraries will return results saying that yes, we have LSTM. Okay, so next advanced level of RNN is LSTM, and people are using LSTMs and GRUs. But then the world has moved on beyond this also, and all these advanced techniques are part of our full length training. All right, so I'll stop here and then we will take a break. After break, we shall get started. It's almost 11:35. So let's be back by. mm, Let me erase everything. Let us be back by 11:45. Break. Please take a break and come back afresh. Yep. Hello all. So let us continue. Yep, order is important, Surya Narayana Raju. Order is important. Uh, Bhanu Prakash, internet issue is at your end, so please fix it. What if neural language original comes in the sequence? That's fine. It doesn't look at only one entry. In your training data, you'll have a lot of entries, Anil. Okay. Can we give time as one of the input to? Yes, you can, Mahesh. After FDP, yeah, for 6 months you'll have access. You can look into that. What if neural comes in sequence? Anil, I told right that you'll have a lot of data, Anil. You'll not have only a single row. If you take a simple newspaper, 1 day newspaper, there'll be different lines, different words. Okay. Yeah, we'll be covering Jivan. Okay. So let us now spend some time on a recurrent neural network and try to understand this. Suppose this is one word that you have, like I'll take the same thing otherwise, one second. Original neural language. So let me say this is original, the word called original. And you're going to have this word of size V. Why same thing? You take the word original and create one hot encoding. Take all the V words in English vocabulary, keep filling zero throughout if that word is not original. Wherever you find the word original, put a 1, rest all will be zeros. Say the second word is neural. For that also you'll have the size, which will be vocabulary. Language, if that is a third word, again the size of this will be the size of vocabulary. Then this input that we are going to have, okay, will be a dummy hidden layer, H0. It's a dummy hidden layer, the first layer, just to maintain some symmetry. That will come as an input to this hidden layer. This word also will go as an input. Okay, and then I'll not speak about this part now. We will speak about this part later. Assume that there is nothing over there. Assume that there is nothing here also. There's nothing there. Okay. Now you take this word, you take an input, and then when you supply the next word to this next layer, hidden layer, the previous word and this hidden layer, both of these will also go as an input. So in some sense, you're storing this word original also and you're carrying it forward. So you're storing it in memory. When you move to the next layer here, what happens? You will any which ways have the neural as input. Alongside that, you will have original. Alongside that, you'll have original and this hidden layer also passing on. And when you move here, this original and neural, both of those combined are going as input to the next layer, and to the next layer you're also taking language. So in some sense, all the previous terms, words which have been used are being carried forward in the network. So you're storing them in memory. Remember the previous example, the history of Spain and France. So what happened is, in the 10th paragraph, when someone says the two countries, your traditional language models and your multi-layered perceptron models will not understand. However, when you use your recurrent neural network, it will store these words in memory and take it forward. So all these words are stored in memory. Next, you'll go give this to the final layer. In final layer, you will have all the words, all the English words, we. And whichever word output has highest probability, that would be chosen as the output. That would be chosen as output. So the first thing that we need to understand here is how many weights is your model learning. V into this size will be H. So V into H. V, and here you have H, VH, V into H, VH. If you have n such words, you'll have n into VH plus. If you look at the weights from this hidden layer to this hidden layer, if you have 4 here and 4 here, every neuron will be connected to every other neuron. We know about this. Then 4 into 4 is 8. If you have H and H into H will be the number of weights that your model is supposed to learn. And final, in this final part, you have H into V. Okay, you'll have H into V basically. Okay, so plus H into V. So if I were to combine these two, it will be N plus 1 into VH plus HH. Weights, right? Let's look at the previous thing. Oh my God, it's N plus 1 into VH only here, the number of weights. But when you look at this, you added an additional component also. So the number of weights are more than your MLP is what you will assume. But the reality is that when you come forward and go backward and update the weights, all these weights, V into H, VH, VH, all these weights you average out and you'll have the same weights here. So even if you have n words, the number of weights that your model will be learning for all of these RNN units. Okay, this is called as one RNN unit. This is another RNN unit. This is another RNN unit. Okay, so you have RNN units. So each of these will have the same weights. So it will be n will become 1 because all these weights will be the same. So you just need to learn VH, that's it. Plus, yeah, here it will be NHH, sorry, NHH, because you have n words, right? 1 H into H, H into H, H into H. How many other words you have? Those many HH weights you need to learn. But then once again, all these words also, HH, all these weights will be the same. So you'll put 1 into HH. Plus, this is anyways VH. So the weights will become 2VH plus HH. These weights are very less in comparison to your MLP, wherein you are learning N plus 1 into VH. Number of words are, if they are 10, then 11 VH. Here it's very less. And hidden layers are going to have less number of neurons than your number of words. And when you looked at your traditional models, it was V raised to the power N. That was even crazy. This you cannot even perform. Forget about it. This you can try out, but again, it has its own share of challenges. Hence, you have this. The best part is the number of weights reduced. Another best part is all the weights, all the words are stored in memory. Okay. And the third best thing here is you are also going to, you can also use this for different contexts. Okay. Just give me a minute, friends. Just a minute. So sorry. Just give me a minute. Okay. Sorry. I will get to your questions in a bit. Our team will answer. Otherwise, I'm going to answer. Okay. So that's how it is. And here, if you have three words and if you want to predict the fourth word, you can do that. If you have four words and if you want to do the predict the fifth word, you can do that. So the beauty here is that your network will expand and collapse. If you have five words, this network will get expanded. One, two, three, four, and then you'll have five. This is how it will be, and you will have final output. You have an input. Okay. If you have five words and if you want to predict the sixth word, you can do this. If you have only two words and if you want to predict the third word, then the network will collapse. It will collapse in this way. And you'll have a dummy hidden layer. Simple. And each of these is called as a recurrent unit. Yep. Now let me get back to your questions. Okay. What if our input word is wrong? Then you have to take care of your input data. Whatever data you have taken, where did you take it from? If it is wrong, why are you even taking it? Would be the question. Okay. I'm clearly saying that you have to take correct data. If you're purposefully taking wrong data, and if you also know that, then rectify it, Revant. Okay. That's how it is. What about the order? Order matters, Venkat. Order really matters here. Okay. Sequence is very important, Venkatakiran. Dr. Mohan asked this question on how we can get multiple answers for single sentence. Okay. If you have a single sentence, how many words will you have in that? You can have multiple, right? For example, if you take this, RAM requirement only scales with the number of words. So maybe you have RAM requirements only three words and you want to predict the fourth word, which is scales. Okay. Next, if you have four words and if you want to predict the fifth word, RAM requirements only scales, it will predict the fifth word. If you have five words or if you have only two words and if you want to predict the third word, you can do that. Okay, if you have 100 words and if you want to predict the 101st word, you can do that. Okay, that's how it works. What about the order at the output? When I say order matters, that's it. How does your data set look like? How does your data set look like? You'll have your inputs and you'll have output. All I'm saying is RAM requirements only. RAM requirement only scales. This is your output. When I say order matters, order matters. This is going to be a one input. Then you might say, no, I want to have only two words and predict the third word. All right, go for it. Take the chunks, RAM requirement, and you want to predict only. Your model will do it, or your algorithms will do it automatically. You need not even worry about this. But internally, this is how the data is structured. If you have four words, then you have to add one more thing here, which will be X. This will become X1, X2, X3, and X4. Okay, then it will look differently. Here, RAM requirement only scales. The fifth one is width. If you want to predict that, if you want to not learn that, that's fine. As part of data cleansing, you'll remove that. Next set of four words will be like this. Requirement only scales with. Requirement only scales with. Okay, the is something, the with will get removed in as part of your data cleansing. So maybe you'll have number. Then take the next set of four words and the fifth word. Whatever sequence you have your data in this, the same pattern your model is going to learn. For example, if you're a professor teaching a subject, whatever you teach to your students will learn only that. Right, professors, lecturers? Think in this way. You're a professor. Whatever input you're giving to your student, based on that, the student's results will come up. Same way, whatever data you are giving and whatever format you're giving your data to your model will learn the same thing. Do not expect magic to happen here. Okay. These are not magic algorithms. These are logic algorithms. Okay. So whatever input you give, the same patterns your model will learn. This is the underlying logic of machine learning algorithms in the first place. Okay. RNNs are better, Sudha. Can we predict next two words at a time? Yep, Revant, you can do that. Anantanath, we will get there. Okay, and you'll have to wait until then. We are still in RNN. After RNN, we'll learn about LSTM. After LSTM, we'll learn about GRU. And eventually, you'll learn about the differences. Okay. Now, let's put some weight into or some logic into this mathematical equation. What's happening here is you'll have a dummy hidden layer, initial hidden layer, and you'll have all these. I'll term this as H naught. Input of the word and this. And then finally you have an output. Hidden layer, output layer. Okay, now here. Current time period hidden layer, say you're here. What is it getting? You're taking an input from the previous hidden layer into the weights plus the current word, whatever you have. Here you'll have xt, here you'll have x. t minus 1, previous word and the current word. So this current word into the weights here, whx, hx, weights. So these weights into this input would give you the output here. Take that output ht into, you'll have weights here also, and when you multiply those and when you apply softmax activation function, you'll get the final output. Of course, at every layer you'll give activation functions, right? Here say you're giving sigmoid activation function. Remember the logic, every neuron will have integration component and activation component. So all these will have neurons. All these will have neurons. So every neuron will have integration and activation. You're doing integration and then you're supplying that to your activation function. Here we are using sigmoid. Here for the final layer, since you'll have many words to choose from, it will be softmax. Okay, next. Here you can fold or unfold through time multiple times. If it is two words and if you want to predict the third word, you unfold it only two times. If you have three words and want to predict the fourth word, unfold it three time periods in that way. If you have a single word and if you want to predict the next word, again collapse it. So you unfold and collapse it maximum times. How many ever times you want. That's the same thing which is given. And the algorithm which is used to update your weights is called as back propagation, same. But since you're traveling back in time by expanding these and collapsing, it is called as through time. So it is back propagation through time. Okay. So you take your zero magnitude vector, hidden layer initially, and move through all the time periods. First time period, second time period, third time period, then probably you're predicting the output here. And you will have words, all the words. Word 1, 2, third word, and then you're predicting the output. The moment you predict the output, you subtract the actual value from the predicted value. And when you subtract the actual value from the predicted value, you'll get error. Take that error and back propagate and update your weights. After you update your weights, here you'll have what? Word into hidden layer, word into hidden layer, word into hidden layer. And here you'll have HH, hidden layer into hidden layer. And here you have H into V. Vocabulary size. Okay, and then that's it. You update all the weights. After you update, take an average of all these. All these weights, you take it and average the weights so that all the weights in these three places is the same. Take all these weights and take average of all these weights so that these weights are the same. And this will have different set of weights. This is how your back propagation through time works. There is a disadvantage also here, which is called as exploding gradient or vanishing gradient problem. Exploding gradient means You'll have all the weights. Okay. Rather than taking this, let me take this recurrent example only. Okay, so you'll have the network in that way, and you'll have the final output. In this, you'll have weights in this, sorry, neurons, and here also you'll have neurons. When you have, say, V neurons here and H neurons here, VH will be the number of weights. If these weights get initialized and if these weights are all greater than 1, then what will happen? Say you have 1.1, the weights, and you have 1.2. If you multiply these two, it will become 1.21 or 1.32, whatever bit. How much would you get? 1.32. Okay. So this is increasing, right? 1.32 is more than 1.1 and 1.2. So if you have numbers which are greater than 1, if your weights randomly get initialized such that if the weights are greater than 1, then the overall output will be much greater. And then if you again multiply it with a number which is greater than 1, it will again become much bigger number. Eventually what will happen is it will become very big, and that's called as exploding gradient problem. So what would happen then? On your error surface, if you're here, you'll overshoot that and go here. So you're missing the value because your gradient or rate of change is exploding. At the same time, we have vanishing gradient problem. If all these weights are initialized such that if they are less than 1, if you multiply these two, you get 0.56, which is lesser than these two. So it'll become lesser and lesser and lesser. So it's going to become so less. What would happen is eventually it will get to 0. So it will update well in the initial time, and then slowly it will vanish off. Vanishing means it will become 0 eventually. Means your algorithm will stop and it will not reach the minimum. This is called as vanishing gradient problem. To address this issue, people use something called as truncated BPTT. So you will say that, do you know what? You can unfold your network back in time only for 10 times, meaning 10 words max, and predict the 11th word. Here also there is a downside, and the downside is that, okay, your model will not be able to learn the entire sequence because you are stopping midway. Same logic, multi-layered perceptron, recurrent neural network, convolution neural network, everything works on the same logic. But here there are a few additional things in your network. And you use cross entropy, which we have discussed. Okay. Let us also discuss about CNN RNN model for image captioning. Okay, even before I get there, questions. I think we are answering that. Yeah, plagiarism has different logic, Dr. Mohan, and yeah, which one is more advantageous? After we discuss LSTM only we can understand that, right, Jayalakshmi? So certainly LSTM, but then when we discuss, we'll understand. Yeah, Sunanda, that will be taken care of. Huh. No, Ganesh, 100% I can tell you that issue is at your side. Once again, I'm going to show you. What is the internet speed? Just take a screenshot of that and send it to us. Yeah, Ganesh? If your internet is not of good quality, if you don't have good speed, you will run into challenges. My internet is pretty stable, almost 100 Mbps. Please check at your end. Yeah, that's what I would suggest, Ganesh Dasari. Please check at your end and do this. Just type speed test it, and send a screenshot to us. If you're using very less speed, etc., then yeah, it would cause trouble certainly. All right, back to our discussion here. CNN RNN can be used for image captioning, meaning if there is an image which is provided, you can give a caption, you can give a label to it. Okay, so here when you have images, your CNN cannot work on your images. Sorry, when it comes to captioning, then CNN cannot work. And RNN cannot work on your images. So how do we deal with this? That is where we take the strength of both CNN and RNN for this. It's like in Kaun Banega Karodpati. Okay, what happens? One person might be very good at history, another person might be very good at politics. You'll make both of them sit together, and when you have to use your lifeline, okay, wherein you can call one of your friends, right? Then you call your friend, and both of them are there. So when people ask question on history or politics, they work well, right? So that's how it is. Basically, you're trying to combine the strengths of CNN, which is very good at dealing with images, and you're combining the strength of RNN, which is very good at dealing with textual data. Now you're combining these two to solve a business problem which is called as image captioning. So what do you do here? Simple. Take your images, pass it to your convolution neural network. But then in your convolution neural network, you have your input image, conv layer, pooling layer. So again you have conv layer, again you have a pooling layer, and then so on and so forth. And then you connect it to you'll flatten it first, and then you connect it to your dense network or dense classifier, and then you have your output, right? So what you do is you train your model until here, take your image, supply it to your model, learn all the weights. These weights will be treated as inputs. All these weights that you have, weight 1, weight 2, weight 3, weight 4, weight 5, all these weights are nothing but your features or inputs. And then you get an output, whatever is your output, right? Take all these weights and this output, pass it to your dense layer here. Instead of the dense layer, you are using dense means what? Multilayered perceptron. Instead of multilayered perceptron, you are saying, I'm going to assign this to RNN, recurrent neural network. And whenever you supply the features that your CNN has learned, features that your CNN has learned, you're supplying it to your RNN. Okay, RNN. So here there are two additional placeholders. One is, I'll show this in programming also. One is to tell to your model that this is the start. You're starting. And the first word that your model is going to predict is straw. Then you take this straw, give it as an input, because in RNN it will get stored in the memory and you supply that as an input. Then next it is predicting that it is hat. So you take that and again pass it on. Finally end. So you'll have a start and an end, which will mark the beginning and the closure of your network, and in between you'll have words. How do I define this? We will do it practically. Don't worry about that now. Just be concerned about theory. So what you do is, you take your image, you pass it through your network, learn all the features, maybe until here or until here, and then what you do is, you pass that to your RNN, and your RNN is going to give a caption to your image. So this is how your model works. Okay. And in order to give image captioning, if you want to train your own model, your own network, if you do not want to use the pre-trained models, then you can go with Microsoft Cocoa dataset. Microsoft Cocoa dataset has 120,000 images. And do you know how it looks like? Like this. Your input is nothing but your image, and your output is the caption. If you have this image, right, this image will be an input here, and the output will be this first one, a man riding. The same image will be input, but output will vary. It is this bicyclist raises his fist. Then again, the same input, same image will be input, output will be this, the dirt biker. Again, the same thing will be as an input, and the output would be this. Again, the same image will go as an input, and the output would be this. So for every image, you'll have 5 sentences. For every image, you'll have 5 sentences each. This is how it works. Simple. In certain cases, your model works well. In certain cases, the captioning, all these are the captions. Okay, in certain cases, the captioning is not appropriate. Now, we have something called as bidirectional RNN. Until now, we discussed about your simple RNN, simple RNN. Now, we will discuss about bidirectional RNN. If you use bidirectional RNN, the number of weights your model is going to learn will become double. So it will take twice the amount of time it usually takes to run your simple RNN. It will take 2 times more time than your simple RNN. Okay, so the network consumes twice as much memory space. Having said this, what is this bidirectional? When do we use it? Say, for example, I say that Ramakrishna is very studious. He asks focused questions. If this is a sentence, if you do only um, forward pass or simple RNN, it works here because it says, okay, Ramakrishna is very studious. He means it is related to Ramakrishna. Wonderful. Your model simple RNN works extremely well if you have these kind of data sets. But what if the data is like this? Having said, I am happy with the training. Having said I'm happy with the training, Ramakrishna sat down. Here, when you do a simple RNN, what would it do? It will only traverse in the forward direction like this. Having said I am happy with the training. But the moment your algorithm looks at I, it is confused because you're moving from left to right. What is this I? Who does this I refer to? We don't know who does this I refer to. And again, if you traverse in this way Ramakrishna, it stores Ramakrishna in memory, but it won't correlate I and Ramakrishna because first it encountered I. Your algorithm is kind of confused. Hence, what we do is we do a bidirectional RNN, meaning you will also traverse in the reverse direction. When you traverse in the reverse direction, down, sat, Ramakrishna, and then when it encounters I here, it knows that okay, it is Ramakrishna. Why? Because it already captured Ramakrishna in memory in the backward direction, in the bidirectional context. And then when it looks at I, it knows that okay, this has to be related to Ramakrishna. In these kind of scenarios, it really, really makes sense for you to use a bidirectional RNN. Okay, so that's how it is. One is your model starts learning in the forward direction, and another is your model also starts learning in the backward direction, in the forward and in the backward. So in the forward direction, it passes like that. You also take the last word and then start training in the reverse direction. This is last but one word. This in this way you traverse. And then finally, when you output, you take both of these and then you give away your output. Both of these and give away your output. Take both of these and give away your output. So the number of weights that you're going to learn would not just be in the forward, but it will also be in the backward direction. You combine both the weights to get your output. Will it be good when it comes to accuracy? Oh, yes, absolutely. Would it be time consuming? Oh, yeah, twice. If you want your model to learn even more better things, even more better, representations, you can also go with deep bidirectional RNNs. Here, you'll have multiple layers, and let me explain deep bidirectional RNN here. One is from the input to your hidden layer, it's the same. So what happens? You go in the forward direction, learn, you take the final word, and then teach your model in the reverse direction. For this, it's fine. But then for the hidden layers, what happens is, in this context, for every hidden layer neuron, it will not have single, it will have both the inputs. So it will have inputs from this forward hidden layer, and in the backward you'll have separate hidden layer. Both of those will go as an input. And here also, in the backward layer, this one, both forward layer hidden neuron and then backward layer hidden neuron, both of those will give us give an input to this. So it'll be even more complicated. It'll just be even more complicated. Okay. Will it take more time? Absolutely, have no doubt about that. Okay, so first thing is try out simple RNN. If it's going to give you the desired result, well and good. If not, proceed with bidirectional RNN. If this works out, well and good. Then try out deep bidirectional RNN. If this works out, well and good. Okay, but then this is the sequence in which you have to do. When it comes to the representations, means the features that your model is going to learn, this is number 1, 2, and 3. When it comes to accuracy, yep, it's the same. But when it comes to speed, if you want some kind of real-time prediction, then the kind of compute that we have currently on the planet doesn't support. Right? And if you want speed, speed will be in this direction. First, second, third. So always when you build your models, you have to strike a right balance between representations accuracy and speed. Always there is going to be a trade-off. Which is better? I cannot say, because maybe you're working with Amazon, prediction should be super fast, or maybe it's a Gmail email that you're writing. If you're writing an email, then speed is more important maybe than accuracy. So you take a call on those lines, business calls. All right. So it's 12:33. So let us take a break, and we are going to again, get started at 12:45. Okay. Until then, we'll take a break. Yep. So yep. So what are the questions? Difference in bidirectional. I think we discussed about that. Bidirectional means it's just in learning happens in two directions. It's nothing to do with back propagation. Okay. Next thing is, can you merge this and device with CNN? Yeah, you can, Srinivas. There is absolutely, all these kind of things should happen and you can do it. Absolutely. Then Dr. Mohan Gandhi says, will the probability accuracy depend on position of missing word in a sentence? We didn't discuss about any missingness here. For example, Oxford researchers have published promising trial results of a vaccine. In this sentence, do the words researchers and vaccine would have same one? Here, there is nothing related to accuracy, probability, nothing, right, Mohan? Dr. Mohan Gandhi? Nothing of that kind is discussed here. It's learning weights. Yeah, your neural network, what does it learn? It learns the weights. If a specific word is appearing more times, more important, it will automatically give more weight or more importance to that. Okay, I mean, I think you will have to go back to multi-layered perceptron and then just understand what the weights learn. Here also the weights are learning some features of your data. Whatever data you give as an input, it's going to learn. Now, nothing to do with two words are close to each other. So will there be more accuracy? No, it doesn't work that way. It doesn't take a single sentence at all into consideration. It takes your entire corpus, entire text data, and then it will process it. Right? Hope you are. Is deep RNN effective than CNN in handling images? Yes. No. RNN is related to dealing with your textual data. CNN is related to dealing with your images. Yeah, RNN is used for forecasting. Yep, absolutely it is used. It is absolutely used. So now let me see if there is anything which is hidden here by any chance, because okay, fine. Anyways, I think that slide, our team would have removed it. Okay. There are many varieties of CNN. One such variety of CNN is called as one-to-one. What happens in one-to-one network is that you take an input and you get an output. Your model just takes an input and it simply throws an output. That's it. Nothing great about it. And then, in what kind of applications do we have this kind of a setup wherein you take an input and you get an output? Is a question that we need to answer, right? And actually, you know what? There are wide variety of such networks which exist. One to one, one to many to many. I mean, in this way, there are many things which exist. So I'm going to speak about those things a bit. One to one means your recurrent unit will have an input and you'll get an output. Simple, one to one mapping. Whenever you use one-to-one mapping, it is not as effective. I mean, why do you even want to use a recurrent neural network for that? Usually it doesn't make sense, right? But then you are taking some input, giving one output. Not very widely used. Second, one to many. One to many means you take one input. If this is your recurrent unit, recurrent unit means it includes the hidden layer and the input. Okay, so, or let me put it in this way. Say you have a word, you're giving that as an input here. This is your dummy hidden layer, anyways, you know that. And then you give an output here, then you pass on, you give an output here, then you pass on, and you give an output here. So you take an input, you pass on, you get an output, output, output. Okay, in this way, in what scenarios can we use this one to many setup? This is called as one to many. In one to many, what happens is you give a starting note of a song. There is a song, you just give the starting note, starting, um, some words, basically lyrics, and this network will automatically produce the remaining words. Provided you train your network on this kind of data set, whatever inputs you give, your model will learn only that. And these weights are going to learn such patterns. And of course, sequences also are important. It will capture the sequence also. And do you know what? Your entire data cleansing is automatically taken care. Your neural network automatically learns that the at, the on, all these are irrelevant words, and it will exclude those. It will automatically do that. So you need not worry at all. Okay, this is one to many. Then you can also have many to one. You'll have an input, another input. You keep supplying your words to this, keep supplying your words, input, input. And then you again take this, give another input, and finally you'll have an output here. So you have three inputs here, input 1, input 2, and input 3, and then you get an output. Okay, this is a scenario. I mean, you can use it in a specific scenario wherein if I give different frames of images, remember CNN RNN models that you can deal with? There, if you give different um, frames of images and the captions to different frames of images, it will finally predict on what should be the output. Okay, those are the things that your model will do. All right, and you can also use it in various other scenarios. I mean, these are all a few things that I'm just giving you. It can be something like movie review. When you have a movie review, you'll have multiple words, and then you need to predict on whether a movie review is positive or negative. So you're having multiple words and you're classifying the sentiment of it on whether given the entire review, is it positive review or a negative review. Not just that, you also have many to many, and this construction that you're seeing here, this network is a classic case of many to many. You give many inputs and you get many outputs. Can you all guess? Can someone guess on in what scenarios can we use this? Yeah, any guesses? In what scenario do we use it? Let's see who will get it right. I'm sure you'll get it right, but then let's see on who is going to nail this. Of course, you would certainly get it right, but I'm just waiting who will get it right. Go for it, friends. Go try. No worries, even if you're wrong. Okay. So you can use this many to many for machine translation. What do you mean by that? You have different words which are given in a specific language, and if you want to output in a different language, you can use this. In fact, slightly different variant of many to many can be used, wherein you'll say that, okay, these are all the input words in German language, and then you have the hidden layers in this way, and what happens usually is if in German language the words might be in different sequence, so outputting the word to word translation in English here will not make sense. So what you do is you wait until here, then you take all these three German words, then you start outputting, then you'll start to output the German words in English in that sequence, in a different sequence. So you'll go here, go here, then you go in this way. That's it. Okay, so let me show you here. When it comes to your English language and German language, the sequence in which you have the words in German would be different than the sequence in which you have the words in English. So first you need to process these words, okay, and only then can you output that, because the sequence is very important. And this kind of a setup wherein immediately as in how you get an input, you classify the output is used for not image classification, but it is used for video classification. What is a video? Video is collection of multiple frames of images. You take this frame, for example, say there is a video which is a cricket video. In first frame, batsman has hit the ball. In the second frame, the ball has gone high in the air. In the third frame, fielder is running under the ball. In the fourth frame, the person has caught the ball. And in the fifth frame, umpire raises the hand saying that it's out. This entire video can be given a caption, video captioning, not image captioning, video captioning, not classification. Sorry, my bad. Video captioning. So here you take each frame, and each frame is processed through your CNN Same things like CNN RNN models. Take each frame, pass it through your CNN, then give it to RNN. RNN will output saying that, okay, batsman has hit the ball. That will be the output. Next frame of image, pass it through your CNN. Whatever the weights your CNN learns, pass it through your RNN. Then it says, ball went high in the air. It would actually give a commentary also. And I know one of the my junior in IIT, who has actually come up with automatic commentary algorithm. You just supply video as an input, and it will just look at that video, analyze the video, and it will automatically give the commentary, AI driven commentary. It's amazing work that this guy has done. Now a lot of people are trying to reuse that. Okay, all right, I think that's good enough from you know RNN perspective. And now what we shall do is we're going to look at the Python programming bit of it. Let me open Anaconda. Of course, we have to do CNN. Sorry, we have to do LSTM. We have to do RNN. There are a lot of things, additional things that we need to do, which we will do. Okay. Now, so here we have the RNN model, and here also if I can to zoom it. So first things first, we are going to now discuss about RNN in further detail. Your question could be on, can I not use CNN for this? Of course, you can try out. We would also try out, right? And then we will be trying out something called as one-dimensional convnet, 1D convnet. Okay, one-dimensional convnet, because when you have an image, you do a 2D, right? Because image is two-dimensional, you need to apply across all the patches. But then if you have a sentence, a sequence in that way, then you apply a one-dimensional convnet on the patches like that. And then you extract the data. Be it document classification, meaning there is a document which is given to you and you want to classify on whether the document belongs to politics or finance, or what does the document actually belong to, which category, is something that you can do. When you have time series data, you can use it for time series also. You can actually identify the author of the book. You can predict who is the author of the book. Okay, by looking at a transcript, speech transcript, you can say who is the person who has spoken. All these things are very much possible. Then you have something called as time series comparison. How closely two stocks, TCS, Infosys, how closely are they stacked together? You can do sequence to sequence learning also. Sequence to sequence is usually used when that means you are trying to convert English to Malay. Malaysia, Malay. You can use it for sentiment analysis. Sentiment analysis could be Twitter tweet or movie reviews. It can be used. Okay, so on and so forth. There are many other examples, but here we'll be resorting to sentiment analysis. And we will also do time series forecasting, not comparison, but just time series forecasting basically. Let me write it here. We will do this also. Two things. And the third thing that we will do is, uh, yeah, I think otherwise let's confine to these two. Let's do these two so that you understand how to deal with textual data and also you understand how to deal with, sequence time series data. All right. Even before I proceed further, quickly I'll look at what kind of questions you asked. Collection of multiple frames is called exactly, Anant. Yes, Kiran. Language processing, Twitter, exactly, exactly. Wonderful, wonderful responses. Okay, wonderful. I think this last question is slightly Venkata Srinivas. Not sure what you mean by that because already I think we discussed around that. Okay, that already we discussed. I'm not sure whether you have focused on this. Training slides are already available. Quizzes are already available. Hands-on will be uploaded in LMS. LMS access will be provided for the next 6 months. By when? If that is your question, I cannot comment. But one thing I can say is before the session ends. Why? Why can't you do it? You might ask me, you might, get hold of me saying that, hey, why are you not uploading? Please upload it. I am with you, friends. I want to upload, but we also have certain projects. Okay, and all of our team members are busy in those projects. So you have to respect us because we are respecting you. Before the session ends, we will upload. Okay, I'm going to ensure ASAP it gets uploaded. However, until then, what do I do? How do I learn? Come on, we have already uploaded the videos on YouTube. Watch those videos and replicate on your systems. And this is what we all agreed because this is how you're going to learn the programming part. If you simply look at the code, if you run line by line, even if you do that for the next 1 year, 2 years, you'll not be able to learn until unless you type. Okay, next. Data sets. Hey, data sets are too large. How are you going to upload? Hold on. We will put that in GitHub. We have already done that. And we will be providing you the link and it will be posted on a WhatsApp group so that it's easy to communicate. Hey, I am not there on WhatsApp group. What do I do? Hold on. Please send a message to this number and we are going to add you to the WhatsApp group. All this is fine. Okay, YouTube videos will have lifetime access. Wonderful. LMS, you're saying 6 months access. Wonderful. But how about assignments? We also want to learn that. Okay. Once you are done with watching the videos and once you're comfortable, do let us know. Okay, do let us know. We are going to give you a link to take the exam. If you get more than 70% marks, simply take a screenshot of that, send it to my email ID, and I will personally help you out. No doubt about this. I will personally help you out. Okay, and immediately I'm going to share assignments with you, and the objective is to ensure that you learn on what is being taught. You learn what is being taught. Hence, this is the condition. Okay. Any doubts on this? Are you all clear? Wonderful. Okay. So if you're not there on the WhatsApp, please do this. A few of you all, the count actually increases now, but that's okay. Um, we can put the link, feedback link there. But then let's continue here. Text is one of the most widespread forms of sequence data. Okay, and here when it comes to question and answers, or when it comes to building a chatbot, we majorly use recurrent neural network. But the disadvantage is that your neural networks, be it recurrent neural network or any neural network, will will not accept the raw text as input. Raw text is not accepted as input. You know that. Neural network works only on, let me put it here, does not work on raw text. This neural network works on only the numeric tensors, only the numbers. So you have to in some way convert your text data into numbers. How do you do that? This process of taking your raw text data and converting your text data into numbers, or I'll put here transforming your text into numbers or into some numerical format is called as vectorizing. Vectorizing is a process of taking your textual data and converting that to numbers. Okay, there are multiple ways that you can perform this task. One is take your textual data and tokenize it. What do you mean by tokenize? Break your text into words. Say you have a sentence such as 360 digit mg is awesome training institute. Here, one way to tokenize is you segment this text, take this text and convert this into words, and then convert each word into a numeric vector. That's one thing. Second thing is you can also divide it into each character. Each of these will become a character. Each of that will become a character. So what you can do is you can take each of those characters, or take your text data, convert that into characters. And then each of these characters can be converted to a numeric vector. Another way of dealing with this is extract n-gram words. So if you want to extract a bigram word, okay, take bigram of words. Words means these two form one bigram. Is awesome forms another bigram. Awesome training is third bigram. Training institute is the fourth bigram. So you form bigrams. So I will put it here. Extract n-grams. You can extract n-gram words or you can extract n-gram characters. Characters also can be done. If you want a bigram character, 360, 60, 0D, DI, IG, GI, IT, TM, MG, all these are bigram characters. First, get that from your text. So take your text, get this. Once you get this, the next thing is you convert this into a numeric vector. Same thing, same thing. And your n-grams is nothing but, as I've told you, it is overlapping groups of consecutive words or consecutive characters. Either you break it into words, or you break it into characters, or you break it into n-gram words or n-gram characters. All these are called as, all these are called as what? Tokens. And the process used to break the text into these tokens is also called as tokenization. Okay, it is called as tokenization. All text vectorization processes consist of text vectorization process consist of applying some tokenization technique. And this tokenization technique will ensure that you convert your text into a numeric vector. And these vectors, these numeric vectors, are then given as input to your neural network. So all these words which go as an input to your recurrent neural network, all these words that go as an input are numeric vectors, numbers, some numbers. And how do we get there? How do I associate a token with a number? Okay, there are multiple ways of associating your tokens with your numeric vector. Vector is collection of numbers, simple. The two major ways to deal with this are one hot encoding, which you all are aware of by now. That's what we have been discussing. But this is not effective, one hot encoding. So the next best way is called as token embedding. Token embedding. Usually, when we split the text, we split the text into words. Hence, this is also called as word embedding. Okay, hence this is also called as word embedding. And throughout our next, we will be only discussing about text. So I can give you an example. 360 digit MG and FDP program. Okay, and I would put it as AP State Skills Development FDP program. Now here, when you want to take this text and when you want to convert this into tokens, how would you do that? Here, 360 digit MG is one token. AP State Skill Development Corporation is another token. FDP Faculty Development Program is another token, and program is another token. So you have multiple tokens. Each of this token, like 360 digit MG, has certain numbers. If it's one hot encoding, what you do is you take all the words in the English dictionary, put it, all the words, and wherever you find this term, you put a 1, rest all will be zeros. But this might not be there in your dictionary. So you have to add another word to your vocabulary. If there are 172,000, it becomes plus 1. This is a new term that you added. Okay, this is simply put your one hot encoding. Very, very simple task. It is not at all complicated. Okay, but then um, you'll have a lot of zeros here, a lot of zeros, and the vocabulary is too large to handle. Hence, there is another variant of one hot encoding which is called as one hot hashing trick. Okay, so what you do is I'll explain about this by running the code one hot encoding. Just remember that I'm going to explain this also. Then we will also learn on how to do word embeddings. Word embeddings means here what happens in one hot encoding is the entire data of one hot encoding will be sparse. Sparse means you'll have too many zeros and only in a single place you'll have one. So this kind of a data set is called a sparse data set. Whenever you have sparse data set, you try to make it dense, and to make it dense, we apply this technique called as word embeddings. Okay, word embeddings on the other hand will be dense. This is one hot encoding will give you sparse representation. This will give you dense representation. How will it work? We'll learn about that tomorrow. Okay, so here you'll have high dimensions, meaning too many words, all the vocabulary. So there'll be too many dimensions. So it is high dimensional. Here it is low dimensional because you'll have very less number of values which will represent each word. So it will be low dimensional. Third thing is it is hard coded, meaning for each and every word you will have this vocabulary, and if that word appears in a specific position you'll put a 1 against that, rest all will be zeros. Here it is learned. You learn it from data. Learned from your data itself. So these are the differences between one hot encoding and word embedding. If you ask me, I personally prefer this. Who doesn't prefer, right? Because one hot encoding will be too complicated to handle. It become very dense. Okay. So just to do a quick recap, we discussed about RNN. We discussed about even before that, what are the language models and what are the disadvantages related to that. Then to counter that, we moved on to multi-layered perceptron, but that also had disadvantages. To counter that, we moved on to neural network, which is recurrent neural network. And in this, one is your simple recurrent network. Next thing is bidirectional recurrent neural network. And the third thing is deep bidirectional recurrent neural network. Okay. So we will learn about word embeddings in a very detailed manner tomorrow, and we will proceed further with RNN. Once we are done with that, we will go to LSTM and GRUs. So last 4 minutes left. The attendance form is given, so questions are being asked. Could you please discuss regional proposal network and bundling box prediction? It's out of scope, Krishna. I think you'll have to maybe register for the main program, or maybe you can drop an email. If time permits, we will see, certainly. Usually you can use word embedding. It depends on the business problem, Ashok, that you try to solve. I think you may not be able to cover the Python code part today. Could you just scroll down so that no, that code has at least, I think, 1,000 lines, Srinivas. You will not be able to replicate it. It has 1,000 lines. Okay, tomorrow we'll anyways learn. Yeah, sure, Anudeep, no problem. Yeah, that's not the actual code, Jagdish. That's just a condensed version. All right. All right, partners. All right, friends. Here is the YouTube link. Please subscribe. Please take it further. Okay, all the videos are there. Once you are okay to take the exam, it's a one take Surya Narayana. If you cannot clear it, if you don't get 70%, then we might not be able to onboard you with respect to assignments. So prepare well. Okay, and then let me know. I'm going to share the link. We'll not share upfront the link. It's not something like it's open book. You'll get different questions each time. Okay. So prepare well. Don't take a chance. It's not going to be walk in the park. We want you all to watch the videos and then attend it. Yeah, that's okay, Aparna. We'll handle it from our side. That's absolutely fine. All right. The feedback link is given to you all. Please provide the feedback and thank you all so much. Stop here. Yep. Thank you, Krishna. Yeah, Revan, tomorrow we'll discuss about that. One hot encoding. I mean, for numbers, you will add additional entries. That's it, along with your alphabets. Thank you all, guys.